Hello viewers, welcome back. In this video lecture, we are going to discuss the synthesis of anthracene and its certain important reactions. Here, first we start with the resonance of the anthracene. So we already learned how to rotate the pi electrons or the pi bonds in the naphthalene. So similarly, we rotate the pi systems here. So here, just here, you see how I am rotating, you see very carefully. So like this. So finally we will get like this. So this is the one. So finally this pi electrons are shifted like this. So like this. Now again I am going to do the second one. You see, this is the first resonance structure and this is the second form. Now if I start from here like this, like this, like this, so wherever the shifted, that I am putting the pi systems like this, like this. If I do this one again like this, like this, like this, so finally we will get the fourth, the resonance structure. This is how we should rotate the pi electrons very sequentially to get the different resonance structures. Okay, next we will move into the synthesis, how we can attain the synthesis of anthracene. So this is one of the important method, Elbs synthesis. Here the starting material is the benzophenone derivative, that is orthomethyl. So here you are heating this one. So what happens is, so this bond, the hydrogen getting cleaved and it forms a double bond. So finally this one shifts and this pi electron shift to this one. So we will get this one intermediate. Later, so this will goes the cyclization. You see, this one it is going to attack and this pi electron gets shifted and this one get shifted like this. Finally we will getting this one. Now this is the very key step. Here whatever this one, this hydride shift, this is, there is a 1,3 hydride is getting shifted to this one and this pi system is getting shifted to here. Finally we are getting this intermediate. Later, so dehydration takes place, so minus H2O by this way. Okay, so like this H2O getting cleaved minus water. So finally we get this anthracene. So this is how this Elbs synthesis occurs. Okay, now next the second method is Haworth synthesis, that we learned similarly the similar way in naphthalene. Okay, though there's a Friedel-Crafts acylation, there we took the succinic anhydride, here we are taking the phthalic anhydride. So benzene attacking, so this one, this carbonyl, and it get cleaved, so we will get this one intermediate. Finally it's getting cyclized by removing the water molecule in the presence of polyphosphoric acid. So we will get, this is the 9,10 anthraquinone. Okay, so later this anthraquinone getting reduced to anthracene. Okay, so this is how our synthesis takes place. The starting material is benzene and phthalic anhydride. Okay, here the first step is Friedel-Crafts acylation. Here second is this is a dehydration followed by cyclization. So we will get anthraquinone and that is reduced with zinc. Finally we will get the anthracene. The third one is Diels-Alder reaction. here we took the starting material 1,4-naphthaquinone. I think you remember that this naphthaquinone can be obtained by, I think, oxidation of this naphthalene with chromic oxide. We will get this naphthaquinone. We learned in this synthesis the reactions of naphthalene. So this is naphthaquinone and this is 1,3-butadiene. So as you know, this in the Diels-Alder reaction, diene and dienophile are the components. Here 1-butadiene, this is a diene, and naphthaquinone is acting as a dienophile. Okay, dienophile. So this diene starts attacking this carbon. So this one going and attack this carbon, and this pi electron shifts. So finally we will get this compound intermediate. This intermediate is getting oxidized with chromic trioxide. So finally we will get this 9,10, that is anthraquinone. The similar way it getting reduced to anthracene. So this is the key step. This is the cyclization, generally by the presence of heat. Thermal conditions, naphthaquinone and 1,3-butadiene getting cyclized to get this product. Okay, so this is the key step. Next one, we are going to talk about what type of reactions the anthracenes it may undergo. So as we learned, this anthracene is a aromatic compound. It will undergo aromatic electrophilic substitution reactions as similar to a naphthalene. Now the question is where this electrophile will get substituted. By observing this anthracene structure, so we are getting 3 unique positions. You see, I marked A, B, C. So that means here there are 3 unique positions. So here this one, even in this case of numbering, this one you can number by this way. This 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so here mostly the electrophile will get substituted at the 9th position. That we are going to see why the electrophile favors the 9th position. Just look at here carefully. When this electrophile is attacked by this anthracene pi system in the 9th system, so we will get this carbocation intermediate. That carbocation intermediate can stabilized by this way. You see, so after substituting this electrophile in the 9th position, you see this aromaticity of these 2 benzene rings remain intact and it is not get disturbed. Okay, but if you do, you can try it in your own, either in the first position or second position like A or B. So if you draw this substituted the electrophile and the resonance structures, you will not get this type of 2 benzene rings aromaticity, the full aromaticity. That's why this 9th position is mostly favorable. Okay, you can draw as many resonance structures. Okay, so like this. This is a double-headed arrow. You should put it very carefully. Okay, if you draw the resonance structures. Now we are going to see different types of electrophilic substitution reactions. Listen carefully. First we are going to see the nitration reaction. Generally we took the nitrating mixture, nitric acid and sulfuric acid, but here we are taking acetyl nitrate. When we are reacting acetyl nitrate with anthracene, this nitro group has been substituted. So this is the way. So it getting attacked by this one and this group will get cleaved. So like this one it will get formed. Okay, so this is the mechanism, and followed by this this electrophile, it form a carbocation and this hydrogen will get cleaved. So that is the step that I already taught you in the this mechanism in the benzene. Okay, the similar way that I am not discussing here in detail. Okay, now why we are selecting this one as a nitrating agent? Because when we use the nitric acid, that nitric acid is also can act as oxidizing agent that will oxidize to anthracene to anthraquinone. That's why we are using this acetyl nitrate as a mild reducing agent. So this is a mild nitrating agent. This is a mild nitrating agent, not like the harsh conditions. If you use the mixture of the sulfuric acid and nitric acid, it will be harsh, but this one is a mild condition, so it can easily substitute whenever any aromatic system is sensitive to that acidic conditions like nitric acid and sulfuric acid. We always use acetyl nitrate as a nitrating agent. That you should remember, that we will discuss in the forthcoming classes also. And this is how the acetyl nitrate will get prepared. That acetic anhydride react with nitric acid, we are getting acetyl nitrate plus acetic acid. Okay, so this is how we should prepare the formation of acetyl nitrate from acetic anhydride. Next reaction that we are going to discuss is halogenation reaction. This also certain typical reaction. You see here we are not using any Lewis acid catalyst. If you remember that halogenation of benzene, there we use some Lewis acid like AlCl3 or FeCl3, like that we will use, but here we don't use. And also observe it, here this 9 and 10th position the chlorine is getting added. Actually this is not a substitution reaction, this is an addition reaction. So we get 9,10 dichloro, 9,10 dihydroanthracene. Both of the chlorine is getting added. Okay, in the both places the hydrogen is there. Okay, here hydrogen and here hydrogen. When we heat with this hydroxide, so this will like take this proton and it will come like this, and this will come by this way, and the chlorine will get cleaved. So finally we will get 9-chloroanthracene. Okay, this is the mechanism how this halogenation get substituted. Initially both the chlorine will get added at 9th and 10th position. Next, the sulfonation. This is also the similar strategy what we learned in the naphthalene. At higher temperature it always substituted at the second position, and the lower temperature it substituted at the first position. Please remember that the lower temperature always the first position, and higher temperature always favors the second position. And also please note that here it will not substituted at the 9th position. So this is the key point you should remember. Sulfonation always getting substituted either first or second. First position favored due to lower temperature, and second position favored at the higher temperature. You see the difference. And the reduction of anthracene, you see here both the 9th and 10th carbon is getting reduced. Here we getting 9,10 dihydroanthracene. See, you check carefully, you have to put the double bonds very carefully. Later the oxidation, here you can use this HNO3. I think you can remember in the nitration of anthracene I told you why we should not use nitric acid, because it will get oxidized, that anthracene will get oxidized. That's why we used acetyl nitrate there for nitration. But if you use the nitric acid, it is oxidizing this anthracene to anthraquinone, that is 9,10 anthraquinone. So this is one of that oxidation product. And next is the very important reaction, the Diels-Alder reaction. So as I told you, in the synthesis of anthracene, the Diels-Alder reaction, diene and dienophile are the key component. But if you see that the diene here, the 9th 10th position, the double bond in anthracene at 9th and 10th position act as a diene, and this one act as a dienophile. So how this always this migration starts from the diene, so it will start going to attack like this, and this one coming and attack this 10th carbon, and finally this one will get migrate. So finally we will get this kind of adduct. You see, this 9th carbon is getting connected here, this one connected to the 10th carbon. So this is called as Diels-Alder adduct. Okay, so these are the key reactions of anthracene. I hope you understand this reactions. Kindly subscribe and share this lecture. Thank you.